Angular momentum. So before you watch this video, it's important that you've watched the torque video, and that is episode 2.1. So make sure you watch those videos before watching this. Also, this lesson is very, very fundamental to understanding the principles that are going to get applied in the hardest problems of this entire course. So all we're going to be dealing with is theoretical stuff right now, and then we're going to get into solving problems. But if you don't understand the theoretical stuff of angular momentum, those problems are going to be very, very difficult to solve, and they will get very confusing. As always, if you like this content, please like and subscribe. Okay, so what is angular momentum? I did introduce this concept in the torque unit, but let's start over from scratch and get into it in detail. We'll start with dealing with angular momentum of a point particle, which is the letter L, and it's a vector, and that's equal to r cross p. Now, because it's a cross product, we have to use the right-hand rule to determine the direction. So we have L, and that's equal to r cross mv, and we know that v is equal to r omega when we're dealing with something that's rotating. So we can replace that with r cross m r omega, which we know that we have mr squared, which we know is I. So if we have mr squared omega, we can replace this with L equals I omega. So for a point particle, we can use r cross mv, but if we're dealing with something like a rod or a disk, we have to use L equals I omega. So this is our basic definition of angular momentum. And we determine angular momentum with the right-hand rule. So we can do the same thing that we've done for torque, and that's why the torque lesson is important. We use our right hand and we curve our fingers from the r value, that comes first, that's our first vector, crossing that in the direction of the momentum. And our thumb points in the direction of the angular momentum. But because we're dealing with circles, what we can do is, if we know the direction of the circle, instead of doing r cross p, we can just make it easier and curl our fingers. And I'll show you an example of that right now. So let's say we have a circle and we have a point out here. And let's say that this mass, we'll call it mass m, is rotating around in this direction clockwise. Then we have an r, and we have our momentum tangent to the circle, so that's rp. And then we would say that, r cross p, or curling our fingers down here, would give us our thumb pointing down. So that's the direction of our angular momentum. So let's do a simple problem. Let's say we have a solid disk, and that disk has a mass of 4 kilograms and a radius of 0.5 meters. And let's say it's spinning at 2 radians per second. And the question is, find the angular momentum. Well, all we have to do in this case, we would use L equals I omega. And we know that I is 1/2 mr squared times omega. And that's going to be equal to 1/2 times 4 times 0.5 squared times 2. And that gives us an angular momentum of 0.25. And the units deriving them from this would be kilograms meters squared per second. and that's our L. Now, what direction is it? It depends on the direction it's rotating. So if it was rotating clockwise, that direction of L would be down. And if it was rotating the other direction, counterclockwise, then our L would be up. So here's one of the first places that angular momentum gets tricky. Angular momentum depends on what point you choose to measure it relative to. In other words, what point are you choosing as the origin? So let's look at a situation where we have a mass m, and it's traveling along with velocity v, and we choose our origin. I'm going to call this point Q. We choose our origin to be in the center of mass of this object. Well, we know that it has linear momentum, and it has linear momentum because it has a mass traveling with a velocity v. But does it have angular momentum relative to point Q? Well, the velocity relative to this point Q, the momentum relative to Q, is 0. So R would be 0 times mv, and so therefore it has no angular momentum. So that makes sense. If we have an object traveling in a straight line, it has linear momentum, but it doesn't have angular momentum because it's not rotating around anything. But we can choose a different value for Q. What if we do something like this? We have the same mass m, and it's traveling with a momentum to the right, say p, and now we choose our point Q, our origin, to be here. Well, now there is a radius that is perpendicular to the momentum. So LQ in this case would be R cross MV, and you would multiply this times that. Now you might be thinking, how can something have angular momentum when it's traveling in a straight line? But think of it this way. What it's doing is it's traveling about this point at that moment around in a circle. Remember in circular motion, we said that the velocity is tangent to the circle? Well, at this moment, if you just took a snapshot of this problem, you would say that this point could be rotating around that point. Therefore, it's acting as if it's going in a circle. Therefore, it acts as if it has angular momentum. So let's do one more situation where we have our point Q origin here, and we have our radius r here to be that distance from the mass, and its momentum is in this direction. Well, now r is not perpendicular to p. So if we know the angle theta in here, then we would say LQ, the angular momentum about point Q, is equal to R cross MV, but not all of R, just this part of R. So we would have to multiply that by sine theta. When we talked about impulse a ways back, we said that J is equal to F net times T, and that was also equal to the change in momentum, M delta V. Well, if we put in delta P for this, what we can do is multiply through by T and rewrite F net as delta P over delta T. Well, if we multiply both sides by R, that would give us R cross F net is equal to R cross delta P over delta T. Well, what is R cross delta P? That is angular momentum. And what is R cross F net? That's torque. So this is how torque relates to angular momentum. Torque is equal to the change in angular momentum over the change in time. It's a rate. And if we want to find out that instantaneous value, we would take the derivative, and that would become dl over dt. So that's instantaneous at that moment. So what if we have a mass, and we'll say again it's mass m, and we choose that point right there to be our origin, our point Q, and we apply a force to it. So the question is, are we going to see a change in angular momentum? Well, this force is applied here, but there's no radius between here and here. So therefore, there's nothing perpendicular to it. So therefore, if we write net torque, and we said R cross F, well, R is 0, so the net torque is 0. Well, what does it mean if the net torque is 0? When we have a net torque, we get a change in angular momentum. So if there's no net torque, then in that case, we would say that the change in angular momentum is 0. And that should make sense. It would gain linear momentum, but not angular momentum. So is there a way to produce a torque and get a new angular momentum? Well, we can use the example we used before, where we have a mass m, and we apply a force here, a net force, and this thing is going to gain velocity in that direction. And if instead of choosing Q in the mass, we choose our point Q here, now we have a force acting perpendicular to a radius. So in this case, we do have a net torque, that's R cross F, and that's going to be equal to the change in angular momentum as a rate with respect to time. And that should make sense, because what's this going to do? Well, again, it's acting as if it's doing this in a circle. It's making it speed up, so at this moment in time, it has more momentum at a radius, so it has more angular momentum. And if we do this net torque, and we say that's equal to RmV, we know that V equals rho omega, and we've done this before, so we can say that becomes mr squared, that was on the page before, times omega is, I'm just skipping one step, I is mr squared. So if we did this for a disk or a rod, that would just be I omega. This is a very instructive problem to solve. Okay, we're not going to put numbers in here. We're just going to talk about ideas. So we have a very massive disk and a very lightweight car. And this car is going to turn on its engine and start to drive. Now, if you can imagine this, as the car starts to drive around the disk, if this is a frictionless axle, then the disk is going to start to rotate in the opposite direction. Now, why is that? Well, the car tires produce friction and push on the disk. So the disk gets a force on it, which is the force of friction, and that's going to be the force of friction of the tires on the disk. But the disk is going to produce friction and push on the tires, so we're going to get a force of friction on the car. So this is on the car, and this is on the disk. So where are these forces? Well, they're at radius r. So therefore, we have a radius cross a force, so we're getting torque. But we're actually getting two torques. We're getting a torque due to this friction, and we're getting a torque due to this friction. So the first question to ask is there a net external torque relative to point Q? Is there a net external torque relative to point Q? Well, let's see. Does this experience a force on it due to this frictional force at a radius r? And the answer is yes. So what's it going to do? If there's a net external torque, it's going to change its angular momentum. And what is that net external torque going to be? It's going to be net equals R cross F, where F is the force of friction, and it's going to change its angular momentum. Why? Because it's going to start to speed up at radius r. So it's going to gain momentum as it starts to spin around. What's the direction of the torque on that? Well, curl your fingers. That's going to be counterclockwise. So if you have a hand, that looks like this. This isn't the best hand. The fingers curl in this direction. Your thumb points up, so L is up. So the car gains new angular momentum up. What about the disc? Is there a net external force or net external torque relative to point Q on the disc? So this was the car. Now we're doing the disc. And let's see. Well, is there a force that's acting on it at a radius? Yes, R cross F. Again, that was friction. This is the equal and opposite friction. So it's going to change angular momentum. So the car starts to rotate in this direction, gaining upward angular momentum. But the disc starts spinning the other direction. So if we take our hand and curl it down, this isn't, again, the best hand, our fingers curl in that direction, we get angular momentum down. So there's a net torque on the car, making the car start to spin with angular momentum up, and the disc gets angular momentum in the opposite direction. So what about the system? Is there a net external torque on the system relative to point Q? And the answer to this is no. Because there are two forces, but they're only acting on the car and the disc. There's nothing else pushing on this from the outside. So if there's no net external force, there isn't any, then we can say that the change in angular momentum has to be zero. Well, how can it be zero? How can the system have no change in angular momentum when we have forces acting at radii, when we have individual net torques, not net torque on the system? Well, that's because the car gets positive L, if we want to call up to be positive, and the disc gets downward L. So we can say that the angular momentum of the system before equals the angular momentum of the system after. So let's make up some numbers. Let's say that the car ends up getting positive angular momentum of 10. We'll just make up a number. That means that the disc must get negative angular momentum of 10. But this does not mean that they have to spin at the same speed, the same angular velocity. So we could say 0 of the car plus the disc, when we're talking about angular momentum here, then these are I omega. So we would say that the car is this little point particle which has a small I, but it's going to start to go faster and faster, whereas the disc, which is negative, has a larger I, so it does gain angular velocity, but not as much. So the value of the system is 0, even though the parts gain angular momentum.
Bart, do you have your slingshot?
No, sir.
I see it in your back pocket.
Just don't stretch it out.
I was once a boy, and like all boys...
You like all boys?
Shut up! A child is in danger under my aegis. Run, Ralph! Run!
Okay.
Time to do what I've never done as principal. Something!
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is So cool. That's the kind of stuff they should teach in school.
We do teach it in school. You're too busy eating sugar snacks and horsing around.
He's right. Learning can teach you things.
Education rules.
Did you ever wonder what this little extra propeller was on a helicopter? Well, it's not to steer the helicopter. The helicopter can actually rotate to be able to get some force due to this to turn. But think about this. This helicopter, once it leaves the ground, there's no friction. So if the helicopter blades start to spin like this, that's going to create upward angular momentum. But there has to be something that conserves angular momentum. We can't have new angular momentum come out of nowhere without having another angular momentum that cancels that out. We can't have a change in angular momentum that occurs out of nothing on a system. So what does that mean? What has to happen? Well, if the helicopter propellers are moving this way, that's going to produce a net torque on the helicopter body. So the helicopter body starts to spin in the opposite direction, producing downward L. So that's what this does. It comes into play to prevent the helicopter from spinning in the other direction. And when you ever watch in the movies, when these get shot down, the helicopter starts rotating and spinning out of control. Another good example of conservation of angular momentum is an ice skater that is spinning on frictionless ice with their hands outstretched, and when they pull their hands in, they start to spin faster. They get a greater angular velocity. Well, you can also see this demo perhaps in a physics classroom where they stand on a disc that's free to rotate, and you take a couple of masses in your hand and you spin around, and then you pull your hands in and you start to spin faster. Well, this is conservation of angular momentum. When your hands are out far, think of mr squared, these point particles are far from the axis of rotation. So therefore, you have a large I. But when you start out, you're spinning slow. Then, when you pull your hands in, I ends up becoming smaller. Your moment of inertia becomes smaller. So to conserve angular momentum, you have to gain angular velocity. Now, we haven't talked about rotational kinetic energy, but just to go over this because it's a question that comes up a bunch. When you pull your arms in, there's a force that's in the direction of the displacement x, which tells us that work is done. So this isn't angular velocity, this would be work. So if work is done, then that means your kinetic energy is going up. So we would say that for conservation of energy, that the initial kinetic energy plus the work done is going to be equal to the kinetic energy final. In other words, the kinetic energy initial is not equal to the kinetic energy final. But if they ask you how does the angular momentum compare, those have to be different. But what if they ask you about the angular velocity? Those are different because the moments of inertia change. One of the directions that we're heading in to solve these problems is ball and rod problems, where a ball hits a rod, maybe the rod's attached to a hinge, or maybe it's in space or on a frictionless table. But before we can do that, let's just briefly review this idea of conservation of linear momentum, because this is going to play into solving those problems. Let's say we have a block on a frictionless table, it's got some Velcro, it comes in, it hits, and they slide off together. Is linear momentum conserved? P lin. Is that conserved? Well, the answer is Yes. And why is it conserved? Because there's no net external forces. Remember, linear momentum is conserved when there's no net external forces. Angular momentum is conserved when there's no net external torques. Okay, but we're not talking about angular momentum yet. We'll do that in just a second. So what about in this situation? I'll put my Velcro in here. So we have a block that's coming in with some velocity v. It hits a second block, but the block has a rod drilled through into the ground so that there is the inability for this block to move. It's glued in place. When this block hits, is linear momentum conserved? Well, the answer is no. And why not? Because this rod exerted a net external force. I'll say it again because it's important. Linear momentum is conserved when there's no net external forces. Angular momentum is conserved when there's no net external torques. So let's look at a ball rod problem. We'll say that this is in space, and we have a ball that comes in and hits a rod. Now, first off, we know that objects will rotate when they're free to rotate about their center of mass. So we can picture that this ball will hit the rod and it might bounce off. It depends on its mass. It might continue on. It might go off at an angle. There's lots of different combinations. But let's just say that the ball hits and moves back at some velocity less than what it came in at. So this v is more than that v. And then this gains angular velocity. But there's also something else that's happening, and that is that the center of mass is translating through space. The center of mass is moving this way, and it has mass, so it gains linear momentum. So the first question to ask is linear momentum conserved? Are there any net external forces on this system? No. There's forces of the ball on the rod and the rod on the ball, but there's nothing outside that's external pushing on it. So we can say that the momentum initial of the ball, the momentum of this ball, has to be equal to the negative momentum of the ball after the collision plus the linear momentum of the rod after the collision. So the momentum of this, that mv and that mv, this mv minus this mv plus this mv have to be equal. This minus that plus that. There it is right there. Okay, but what about angular momentum? Well, the question we ask is, are there any net external torques? Well, let's choose this as our point Q because it's going to rotate about that point. So there is a net external torque of the ball on the rod and of the rod on the ball, but on the system there are not. So angular momentum has to be conserved. What's the initial angular momentum? Well, that's going to be r cross mv relative to point Q. What's the angular momentum going to be afterwards? Well, it's going to be this value, and that's going to be r cross mv again. The rod gains angular momentum because it then starts to spin in this direction, and that's going to be I of the rod, 1/12 ml squared, times omega. So our L initial has to equal our negative L final of the ball plus the positive L final of the rod rotating. This one is extremely tricky. Let's say we have a ball that's coming in and hits a rod in space, and then it sticks to the rod. Well, what's going to happen? Remember back, all the way back when we did center of mass, that objects rotate around their center of mass when they're free to rotate. We don't put hinges or axles in them. So a rod by itself would rotate around its center of mass. But when this ball hits the rod, the center of mass has shifted. So there's the center of mass of the rod by itself. Depending on the mass of the ball, the center of mass is going to be somewhere between here and here. So let's just say it's here. It's not necessarily in the center. It's somewhere along this line. And we could do our XCOM formula to figure that out. So what's it going to do? Well, now it's going to rotate around this point. So that means when we calculate radius, we're going to make that our point Q. And wow, is that tricky, because you have to make sure you're getting the right L, which is your R, right here. So the first question is linear momentum conserved? The answer is yes, because there's no net external forces. Now think about that. What is going to be the direction of the linear momentum? That is going to be the velocity of the center of mass times m. That's going to be our momentum. So the momentum of the ball comes in, that's going to be mv. And then this is going to be mv, and that's going to be m of the ball plus m of the rod, all times velocity of the center of mass. And we have to go out of our way to find that center of mass separately unless they give it to us. Is angular momentum conserved? Are there any net external torques? The answer is no. So angular momentum is conserved. And for this, now we have to choose our angular momentum. But this is not our point Q. Our point Q is our new center of mass. So when we calculate this L, our R is going to be that value. And we have to do the same thing when we calculate the rod. So L of the rod is then going to be the rod rotating about that point, not about the center of mass. And one last problem. This time we're not in space. We have gravity acting down, so this is a hinge maybe connected to the wall. And this hinge is holding onto this rod, and the rod is free to pivot, sort of like a pendulum. It's called a physical pendulum. So we have this ball that comes in, it has some mass m. And the first question is linear momentum conserved? Well, are there any net external forces? This time, the answer is yes. The hinge exerts a force this way. So that means linear momentum is not conserved. So we cannot say we can use that formula. But can we use angular momentum? Well, let's see. If we choose this to be our origin, we have a force of the ball on the rod and the rod on the ball at radius r, but this force is at point Q, which is 0 radius. So that means this doesn't matter, which means that linear or angular momentum is conserved. Yes. So what do we have then? We have the angular momentum of the ball, and that's going to be mv at this radius r. Then we have the negative angular momentum of the ball, because it's going in the opposite direction, plus the angular momentum of the rod, and the rod is spinning about here. So when we do that I, that's going to be 1/3 ml squared for a rod rotating about its end.